Arthur Perkins.
I'm Kevin Burkett.
I'm Brad Cox.
I'm Tara Klein.
And this is the CS10 Battery Management System, Senior Design Group 6, 2011-2012. The battery management system is designed specifically for nickel metal hydride batteries, which is unique among the market. It is additionally designed for use in electric vehicles. The design goal was for a simple, low-maintenance, user-friendly system. The additional goals were to provide accurate voltage and temperature data on battery cells and to provide safety measures for the user, the vehicle, and the system. The currently implemented features are a graphing system for the voltage and temperature and a smart charging subsystem to protect the batteries. Now on to Kevin for the hardware.
The CS10 system is designed with 3 boards: a bypass board, a data acquisition board, and a controller board. The bypass boards are connected to every 3 cells, so the number of bypass boards in the system depends on the size of the battery pack. Each bypass board is able to bypass 1 amp current when the cells reach the nominal voltage set by the user. The bypass boards connect to the data acquisition boards. Each data acquisition board can monitor 12 bypass boards. So again, the number of data acquisition boards depends on the size of the battery pack. The data acquisition boards also connect to 2 thermistors that are placed on the battery packs to measure the temperature of the cells while they are charging. Each additional data acquisition board communicates laterally with the previous board using I²C. The data acquisition board connects to the microcontroller board using I²C. All the data collected by the data acquisition board is sent to the microcontroller and then sent to the computer using RS-232. The controller board is running a Freescale microcontroller on a Thunderbird 12 DIP module. The reason we use a DIP module is because it was simpler to code and debug for this prototype system.
The microcontroller board communicates to our Windows application through RS-232. The application allows the user to create a configuration file with the nominal charge voltage, maximum temperature, number of modules, and cells in those modules. The user can save this configuration file to load it later. The application shows the voltage and temperature measuring in real time to the user in a bar graph. These values are saved in a CSV file for the user to analyze or use at a later time.
I'm Brad, and I'll now go through the key components on each of the 3 PCBs. The bypass boards are mounted to the nickel metal hydride batteries using 2 plastic 1032 1-inch screws. The board is connected to the terminals of the batteries using 22 gauge wire with ring terminals. The bypass board contains an external MOSFET which bypasses current around the cells through a 3.9 ohm 5-watt resistor. A red LED is in parallel with the resistor for notification of bypass activity. The bypass boards are connected to the data acquisition board through an 18-wire connector. The data acquisition board contains the Maxim 11068. This chip measures the voltage and temperature of the nickel metal hydride cells. 2 5 kilovolt isolators are used to protect the system from the high voltage batteries. The jumper pins located at the bottom of the board are used to bypass the isolators and must be used on every board after the first board. 2 6-pin Molex connectors are used for communication between boards. The data acquisition board connects to the controller board through the Molex connector located at the bottom of the board. This board contains a 60-pin socket which holds the Thunderbird 12 DIP module. This module contains the Freescale microcontroller. The integrated circuit on the left is the Max RS-232 chip. 2 reed relays are used to trigger a MOSFET to change the mode of the charger. Red LEDs are used to notify when the relays are triggered. The power switch located on the left must contain a jumper in order for the board to receive power. A serial connector located at the top of the board is used to communicate with the laptop.